calculating the current in a single loop circuit. This is a single loop circuit. Okay? We use the energy method. This is energy produced in an electromotive force device equal to, by definition, the W it works done is epsilon dq. It moves dq from negative to positive with the work dW. Okay, and the dq from this point of view is I dt. This work done by the C. And Q equal to I squared R dt, okay, is the thermal energy dissipated from the resistor. Okay, I squared R power multiplied by time dt is Q. They should be equal because of energy conservation. So we make this EI dt equal to I squared. And we get I. I equal to epsilon for R. This is for ideal electromotive force without internal resistance. And actually, they have internal resistance. So the I equal to epsilon over R plus R. R is the internal resistance of the electromotive force device. Second, we use the potential method. We have a loop rule. The algebraic sum of the changes in potential encountered in a complete travel of any loop of a circuit must be zero, because the same potential at the beginning and the last, so the potential difference is zero. Resistance rule. For a move through a resistance in the direction of the current, the change in the potential is minus IR. In the opposite direction, it is positive IR. Now, we look at this current, I, and resistance. Definitely, this is a high potential, this is low potential. If we go so along the I direction, the potential goes lower, that's minus IR. If we go this direction, look at it, the potential goes high as IR. Electromotive force rule. For a move through an ideal electromotive force device in the direction of the electromotive force arrow, the change in potential is plus epsilon. In the opposite direction, it is minus epsilon. Now, we go along this direction, the potential increase, epsilon. If we go this one opposite the direction, we get a minus epsilon. This is a single loop circuit. Okay, we can assume a current arbitrarily. In this case, we assume it's clockwise. Of course, you can assume the opposite direction arbitrarily. We also can assume a direction, a transverse arbitrarily. You can calculate in this direction or opposite direction. We get the same answer. Now let's try this one. We suppose I is this direction as indicated in the book. Starting from point A, we go this along the direction of this arrow, we get the potential increase. We go this direction, okay, clockwise, increase. And go this one, so the resistance along the direction of current, get a minus IR. And we go to a 0. From this one, we get I equal to epsilon over R. Now, we do different. We don't go this way. We go opposite direction. Can we? We go counterclockwise. I start from A. We go against I, we get IR. And we go against epsilon, get a minus epsilon. So plus IR minus epsilon, we get I equal to. So they are the same. The answer does not depend on the direction you choose. Okay. Now we do different way. We assume the opposite current. Okay. And not this direction. Go opposite direction. Okay. And what happened? And we start from here. We can choose anyway. Okay, now we choose the clockwise, this one from A. So we go to epsilon against I plus IR go with 0. Okay, epsilon. And you get I equal to minus epsilon. Or, you see, well, this is positive and negative. Is the same or not? It's the same. Why? Because in this case, you assume the current this way. So that means real current is this way. And here, we assume the current this way. You get a negative number, that means real current is this way. The same as the previous answer. Now, under this conception of current, we do another transverse. Okay, we go counterclockwise. We start from A, go this one. This should be minus IR. This should be minus epsilon. Okay, we get I equals. Under this assumption, we get the same thing. Okay. Other single loop circuits. This figure shows a real battery with an internal resistance R wired to external resistors of resistance R. And analyze this one, start from A. We start from A, okay, we go to battery, so the potential goes up. Okay, this is potential. And we go so the internal resistance equal drops, okay, because this is minus IR. And when you go this along the current, get another minus I, and go back to the original VA. So VA plus epsilon minus IR minus my big R, you get VA. You cancel out VA, we get R equals epsilon over R or R. That's the one we just mentioned, okay? Potential difference between 2 points. I want to find the potential difference between 2 points, like B and A. From B to A, okay, I go this one, okay, VB, okay, I go this direction, minus IR, because I go so equal to VA. So VB over VA equal to RA, IR, okay? Also, we can go this direction. This direction is this plus IR minus epsilon. We get the same thing. You get the same thing. So equal to I over R. This is I over R, I equal to epsilon over R plus R. Okay? To find the potential difference between any 2 points in the circuit, start at 1 point and transverse the circuit to the other, following any plane, and add algebraically the change in potential that you encounter. You get it?
These two sets of batteries appear identical and show approximately the same reading on a voltmeter, but there is a difference. When a light bulb is connected to this set of batteries, the bulb lights and the voltage of the batteries remains about the same. When we do the same with this set, the bulb fails to light and the voltage of the batteries drops to nearly nothing. This set of batteries has been heavily used and has a high internal resistance.
We'll hook these 3 variable resistors in series with this battery and measure the voltage drop across each resistor to see how their sum compares to the applied voltage. The battery supplies a constant 6 volts. Let's go around the circuit and measure each of the voltage drops. The first resistor has a voltage drop of minus 0.9 volts. The second, minus 2.6 volts. And the third, minus 2.5 volts. The sum of the voltage drops, minus 6 volts, is the opposite of the applied voltage. Now we'll change the resistors and repeat the process. The first resistor now has a voltage drop of minus 2.2 volts. The second, minus 3.5 volts, and the third, minus 0.3 volts. The sum of the three voltage drops is again the opposite of the applied voltage.
Resistors in series, we have learned in high school. If we have three resistors connect in series, we can use an equivalent resistance, replace them, okay? And this number of equal resistance could sigma IR.
We'll hook these two identical wire resistors together in three different configurations and apply the same voltage to each. This ammeter will measure the current that flows through each of the configurations. Here is the current that flows through a single wire with 6 volts applied. If we hook the two wires in parallel, how much current will flow? Twice as much current flows as with a single wire. If we hook the wires in series, how much current will flow? Now only half as much current flows as through a single wire.
Here are 3 light bulbs. We'll hook the first bulb up to house current, then hook the other 2 bulbs in parallel to the first, one at a time. The brightness of the bulb stays constant as each is hooked in. Now we'll again hook up the first bulb, then hook the other 2 bulbs in series with it, one by one. How will the brightness of the bulbs change? The bulbs dim as each new bulb is added.
Resistances in parallel. We also learned in high school. We have 3 resistors connect in parallel, and you can use equivalent resistance to replace these 3. Okay? And the relationship between is 1 over R equivalent equal to sigma 1 over Ri. Sample. The electromotive force and the resistance in the circuit in figure have the following values. Epsilon 1 equal to 4.4 volt. Epsilon 2 is at 2.1 volt. R1 2.3 ohms. R2 1.8 volt. Big R 5.5 ohms. Question A. What is the current I in the circuit? And this is very straightforward. Okay. We look at this. Okay. We from 8. Okay. We go counterclockwise from 8 to this one. So the first one goes, we drop epsilon 1 minus epsilon 1. Okay. We assume the current in this direction. So whatever you can assume, as we mentioned before. So this one you come from up to down against the current. So you get plus IR. Okay. You go this one. You go to epsilon I1, big R, R2, and then second battery, you go to 8. And what we do is, we the counterclockwise this way, okay? This is minus epsilon. This is positive IR, positive I, big R, positive IR2, and positive epsilon 2, okay? So in this way, we can get I, get the I, okay? This is actually, you get dropped potential. You got increase, you got increase, you get an increase, and you have another increase, you get the same level. We find I. Epsilon 1 minus epsilon 2 over R plus I1 R2. Also, we can do different way. Okay, we go clockwise. At the 8 clockwise, it goes, this is minus epsilon 2. This is along this one, minus I R2, minus R big I, minus I R1, and you plus epsilon 1. And so you go this way, you get I, the same as the previous, because you assume the same direction of current. Question B. What is the potential difference between the terminals of the battery 1 in figure? This is the one, battery 1, or these two. That's, you know what to shoot. VB. This is VB. Okay, you go this, along the current, you get a minus IR1. You plus epsilon, you get VA. Okay, so VA minus VB equal to epsilon minus IR. And then we know I. Okay, we just calculate. So we put the number inside. Okay, we get answer 3.84 volt.